Hi, my name is Josh Chavez. I'm a processing engineer at Hawkeye 360. Welcome to Hawkeye 101. As you probably already know, at Hawkeye 360, we look at radio frequency signals. That's because much of our digital world today is powered by radio frequency waves, which means we can access a wealth of information about global trends and activities by looking at radio frequency signals. But what is radio frequency, or RF, and where do RF signals come from? Let's back it up and first look at the electromagnetic spectrum, which is the entire range of electromagnetic radiation, or energy, in the universe. The electromagnetic spectrum is made up of several types of waves of varying length and frequency. The waves in the electromagnetic spectrum that our eyes can see are called visible light. But there are several other types of electromagnetic waves outside our field of vision, such as ultraviolet light, X-rays, gamma rays, microwaves, and of course, radio waves. Hawkeye 360's constellation of satellites specifically identify and geolocate signals from the radio section of the electromagnetic spectrum. We can further divvy up the radio spectrum by frequency into what's called spectrum bands. In the near term, Hawkeye 360's constellation of satellites is designed to detect the range from VHF to Ku band. Within each spectrum band, there can be many types of emitters that operate. Some RF emitters that Hawkeye 360 frequently detects are push-to-talk radios, mobile satellite devices, automatic identification systems, and maritime and coastal radars. We often call the emitters we detect signals of interest. So, how do we geolocate these signals of interest? We use clusters of satellites rather than planes, drones, or land-based collection systems, so we can observe thousands of kilometers of Earth's surface at a time, or entire regions of the world. Our clusters fly in triangular formations in low Earth orbit. As each satellite passes over a signal, it records details about that signal's waveform, such as what part of the radio wave hits the satellite and exactly when it hits the satellite. We compare these tiny differences between all three satellites using equations that calculate the time difference of arrival, or TDOA, and frequency difference of arrival, or FDOA. This allows us to pinpoint signal locations with high precision, as close as a few hundred meters. Our choice to fly clusters in formation creates optimal geometry for accurate geolocation. We also apply proprietary signal processing algorithms on top of the basic TDOA and FDOA equations to further refine detection and accuracy. Today, our satellites can detect a growing library of signals of interest. While we can detect RF signals with high accuracy, day or night, in any type of weather, the accuracy and detection of individual RF signals depends on a few factors. These include the type of RF signal, the distance between an RF emitter and our satellites, the type of antenna used by the emitters we're detecting, and noise in the spectrum, or how many emitters are active in the frequency we're looking at in the area we're looking at. Think about attending a concert. If you're in a large crowd at a rock concert with thousands of fans, it would be incredibly difficult to pick out one individual's voice from the roar of the crowd. But if you're one of a handful of guests at a small acoustic set, it would be pretty easy to pick out someone from the crowd if they choose to talk mid-show. Once our satellites downlink their data to a secure cloud environment, we can further examine characteristics of the RF signals we collected to add invaluable contexts for mission analysts. For example, by looking at different attributes of specific RF signals, we could distinguish between types of UHF and VHF push-to-talk radios, such as digital mobile radios, terrestrial trunked radio, or MPT 1327. We could also distinguish between L-band mobile satellite carriers, such as Thuraya and Inmarsat. Added information like this is important as it can help analysts make more educated guesses about why an emitter is being used. For example, if an analyst sees a geolocation for a radio in a certain area, and that analyst also notices that that radio is using a channel that's not authorized in that country, he or she might conclude that the radio is involved in unauthorized or unusual activity that warrants further investigation. Commercial RF signals are a relatively new data source that can provide us with invaluable insight into global activity. However, only a small subset of the geospatial intelligence community has been able to fully understand and use this resource without support. Now that you have a general understanding of RF signals and how we detect them, it's time to put that knowledge to use. Watch the next video in our Hawkeye 101 series to see how you can understand and use this new source of intelligence.